Stacks of thin films can be used to realize various components, including mirrors, optical filters, and beam splitters. We start to use our T matrices by analyzing a single film on a substrate. This is about the only structure which can be analyzed analytically. More layers are convenient to be analyzed with numerical methods in MATLAB. The layer on a substrate consists of two interfaces. It can be described with two interface matrices and one propagation matrix. The full T matrix can now be calculated from their product. The individual matrices are R12 is the reflection coefficient of the first interface, R23 is the reflection coefficient from the second interface, and Kn is the normal component of the wave vector in the layer. And when we calculate the product, reflection for the single film can be easily identified from this matrix as the ratio of the elements M21 and M11. And now we have an analytical solution for the reflection of the single film. One of the most important applications of thin films are anti-reflection coatings. With this formula, we can now analyze how does this work with a single film on a substrate. If we wish to completely suppress reflection from the substrate, we set the denominator of the equation for the reflection to 0. In direct incidence, we can write the reflection coefficients as we are seeking real solution for this equation, and therefore the complex phase factor should be either plus or minus 1. To get a non-trivial solution, we need to select the minus sign. Therefore, the phase of the exponential function should be plus or minus pi. And this condition gives us a relation for the needed thickness of the anti-reflection coating film. And as we see, the thickness is quarter wavelength thick film. Notice that we can use this form of the equation to determine the optimum thickness of the film, even if the angle of incidence is different from the direct incidence. And in this case, we write the normal component of the wave number as, and this is called angle-matched quarter wave thickness. The refractive index of the film to realize anti-reflection coating can now be solved from the remaining equation. As a result, the index should be square root of the product of the refractive indices of the first and the last layers. And as a summary, if we want to realize an anti-reflection coating with a single film, it needs to be quarter wave thick and have such refractive index. Let's take an example. Assume we have a silicon substrate and it has a constant refractive index of 3.5. Now we can calculate the needed refractive index of the layer. If we design the anti-reflection for the wavelength of 300 nanometers, the thickness should be about 68 nanometers. And from the figure, we see that indeed the reflection is 0 at the design wavelength. It has dropped from initial value of around 30% significantly. By using some more complicated layer structures, the anti-reflection property can be modified. And usually we want very broad wavelength range operation.